if I look at a profile of the velocity of water, it looks something like that in a stream. And it's flowing this way, and it is applying a stress to the bottom of the channel. And the channel, actually, I should say, it is pulling the bottom of the channel that way, tugging on all the rocks at the surface. And then the channel is the bottom of the surface of the earth, the bottom of your channel or the beach or whatever it is tugging on the bottom of your stream and slowing it down. And that causes energy loss. And we got here, and we figured out that there's this thing called roughness, that the rougher the channel is, the greater the shear stress, and the greater the velocity, the greater the shear stress. And so here's our first shear stress. There we go. Here's our shear stress equation, where shear stress equals this shape and roughness factor times the density of the fluid, not the density of the sediment, times the velocity squared. So if I double velocity, I multiply shear stress by 4. Aha. If I increase the roughness, remember this is a kind of a cool thing. Let's pretend we're in a stream channel and it's flowing downhill, and we have nice little smooth sand on the bottom, and then all of a sudden I have some big angular boulders. What's going to happen to this F value here as we go from the sand to the big rocks? It's going to get rougher. It's going to increase. And if we're looking at a level here, and here's the surface of our water, it's going to decrease as it goes over the sand, and this decrease in energy, remember that we can represent energy as head in the stream, so the loss in elevation in a stream is a loss in energy. And but it doesn't have to lose energy that way either, right? It can also lose energy by losing velocity. So it can slow down and lose energy, or it can go downhill and lose energy. Does that make everybody cool with all of that? Don't want to. Anyway, so here it is, losing energy. It hits these rocks, and what's going to happen is, here's how fast it was losing energy before. It's going to start losing energy faster. So the rougher a stream is, the faster the surface goes downhill, because it loses energy. And so if it at the same velocity, right? The other thing it could do is, well, it's not going to go downhill very much, so it's going to just lose energy by losing velocity. It's going to slow down that way, reduce shear stress. Well, if we've got water going fast here and slow here, what's going to have happen? It's going to get deeper, right? Because we're piling up water here. So the water will get deeper. It won't suddenly jump up like that, but over the rougher parts of the channel, it will actually get deeper. And so you'll have greater depth over that. And it will keep doing that until the shear stress and velocity and roughness are all in balance. And that's what beaches, streams, any sedimentary environment does. It balances the shear stress on the base with the roughness of the channel bottom and the velocity of the flow. You increase roughness, you increase shear stress, velocity has to adjust to that. Okay, and say that if we increase roughness, well, the shear stress increases, that slows down the velocity, which will then cause the shear stress to reduce until these are back in balance. Okay, is all this making sense so far? Okay. Anyway, this is just a calculation of that. So the thing is now we're going to spend this class, or first half of this class, looking at exactly how that shear stress is applied to the fluid. It's really fun. How many of you guys have studied boundary layers and things like that before? Anybody done any hydrodynamics or fluid mechanics? Okay, cool. This is fun. Very non-mathematical part of this lecture. It's, I have there we go. So I have all these videos. There are lots and lots of videos on the web. Some of them are unbelievably boring, and some of them are pretty good. But here is a good analogy. This is what engineers do. This is like they've got like two metal plates, and then this is smoke traveling through the air around the metal plate. And here they have a little obstacle so that the fluid, the air in this case, has to go around the obstacle. And notice that what's happening is these are having to be compressed, which means they have to go faster to get around the obstacle. So that's the Bernoulli effect. And so this would actually be applying a lifting force that way and a lifting force that way. And it would also be applying a shear stress to the fluid and to the obstacle. It would be tugging the obstacle this way and tugging the fluid that way. Oh, before I do anything else, this guy's so unbelievably boring.
In a real fluid, water, flows around the same shape. The flow is quite different.
Okay.
Boundary layers, thin layers of fluid in which viscosity affects the flow dynamics, are formed.
Okay. So here's like just a plate of glass. That is the boundary layer. And if you look at it carefully, you'll see there's all sorts of things going on in there. So
formed along the surfaces of the object. The behavior of these boundary layers under the influence of pressure gradients can, in some cases, drastically alter the flow. The streamline pattern is very nearly what one would predict from an inviscid flow theory. Because the Reynolds number is large, influences of viscosity are confined to a narrow region close to the surface of the wing. The primary effect of viscosity is simply to create a drag force on the wing through the integrated effect of surface shear stress.
okay, let's stop there. If you think about it, if I have air blowing over this wing, it's going to go over the wing and not tug on it very much. If I have Karo syrup, and I'm having Karo syrup flow past this wing, it's going to pull hard on the wing, right? And it's also, that wing is going to have much more drastic effects on the syrup. The difference between air and Karo syrup are two. One is density, the syrup's heavier, and the other is viscosity. Viscosity is the ability of a fluid to flow smoothly across anything. It is the ability of a fluid to deform internally. And so fluids with low viscosity, you can move material through the fluid and it just slides right on through, or if you shear the fluid, doesn't take much effort to do it. Highly viscous fluids, it's harder to get them to shear. So a good viscous fluid, think mud or syrup or heavy motor oil.
As the angle of attack is increased, viscous effects become more pronounced. Pressure gradients imposed on the boundary layers become more severe, and separation occurs on the upper surface.
Okay, separation is something that we deal with a lot in geology. This is separation, we're going to see it, where the fluid separates from the surface. And so you have a region behind here. This still has air or water in it, but it's what we call an eddy. It's not moving anywhere. It's just sort of circling around. So, cool, everybody? Okay. This is actually in what causes airplanes to crash. When you have separation on top of an airplane wing, that's a stall. When airplanes take off too steep, they lose lift when this happens because the air is no longer pulling on the top of the wing. I'm going to skip ahead. Let's see. There's one I want to show you here that's pretty cool. Ah, there it is. This is fun. It's for the beginning of it.
These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timeline, the vertical patches of bubbles, remain perpendicular to the streamline shows that the unobstructed flow is free of vorticity. Here is the flow over a plate.
All right.
The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present.
See how it's...
In the narrow boundary layer region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected.
Okay. If you look at a fluid, here, let me stop it when it's halfway through. If you look at a fluid, and if you look at the top of this, that's like a river channel or a wave passing over a beach. And what if you look at the fluid, you have, can you guys see okay over here? If you look, you've got have a stream bottom, and then you've got the fluid, and this is just like a big block of fluid going on. This is the bulk of your river. And as you get near the bottom, the velocity decreases, and it decreases more abruptly as you get down near the bottom. And we call this zone where the velocity of the flow is changing rapidly the boundary layer. And if, like here, you have a very viscous fluid, very viscous, or the fluid is moving very, very slowly, you have what's called a laminar boundary layer. And in a laminar boundary layer, it does just what's going on here. The fluid, one layer of the fluid slides over the other smoothly, so that the bottom layer is moving, well, the bottom layer against the bottom is not moving at all, right? Those molecules of water are going to be stuck to whatever they're on. And then a few molecules up, you'll have a layer of water that's moving slowly. And then above that, a layer of water that's moving a little faster. And above that, a layer of water that's moving faster. And above that, a layer of water moving faster. And that's what you're seeing there. And that's called a laminar boundary layer. And right next to, even, it really doesn't matter, right next to whatever particle it is, where things are moving really, really slowly, you'll have a little bit of laminar boundary layer. And that's called the viscous boundary layer, where the fluid is moving so slowly because it's just a molecule or two away from the particle. It's sliding so slowly, it's still making a laminar boundary. Does that make sense? Okay. Cool. Let's move along then. Hopefully, okay, now we'll move on to something different.
The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. So
the more viscous the fluid, the thicker the boundary layer.
Moving the camera with the free stream velocity will give a better view of the layer growth.
Isn't that cool?
You said this is smoke?
Huh? It's hydrogen bubbles in water. They used electricity to turn water into oxygen and hydrogen. And those bubbles of hydrogen, teeny tiny bubbles of hydrogen are what you see.
There is no slip between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero.
So that's what I just said.
No slip boundary condition of viscous flow.
Viscous boundary layer.
The bubbles corresponds closely to the velocity profile in the boundary layer.
And it gives you a parabolic boundary layer.
Thickness of a boundary layer is sometimes defined as the distance delta.
And we're going to,
Surface to where the
we're not going to worry about that.
Some fixed percentage of the free stream value.
Let's see.
For our purpose, we will use 95% of.
Okay, here's the sim. I want to get to something